I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Okay, Jam, how are you feeling today?
I'm feeling good. I'm a little worn out. It's the end of the day, but I've got some coffee and I'm ready for chemistry, ready for learning, because even though it's kind of work for my brain, it's different than what I've been doing all day. So I'm down.
Nice. I am feeling kind of summery today.
Whoa, you don't feel summery.
Yeah, I know. But I'm feeling it. I did my work outside.
Uh-huh.
And it was kind of hot.
Totally.
And I was eating these nice Lay's kettle cooked jalapeno chips that my friend.
Man, dude.
Mm-hmm.
Gosh.
So good. My friend Roxanne turned me onto those.
Yeah, they're very, very good. Roxanne is a good friend.
She really is. So I was doing that, sitting outside, doing my work, eating my chips, and thinking about jalapenos. And I don't really like jalapenos, but my brother asked me a long time ago about jalapenos and why do they feel hot.
Huh. Feel hot in our mouths kind of thing.
Mm-hmm.
Okay.
And we're going to talk about the specific thing that makes them feel hot, what that molecule is. He already knew the name for it, and so he asked, why does that molecule feel hot, was his exact question.
Interesting. He knew part of it. It's crazy.
He already knew part of it, and he also puts jalapenos a lot in his amazing guac. So that's a really summery thing also that I eat. So it just all came around to this summery feeling.
Yeah. Interesting. Dude, that's awesome. You're summer. Let's take advantage of it for sure.
Okay, so a lot of people already know what makes peppers hot, but there's more to it than just the surface. We're going to talk about that. We're also going to talk about that there's a little bit more to it.
Mm-hmm.
And we're going to talk about if you can build up a tolerance to hot peppers.
Whoa.
And we're going to talk about why people tell you to drink milk.
Interesting. Here's where I'm at. I don't know anything about it.
You know nothing?
I know nothing about the, like you said, your brother knows the molecule that makes it hot. I don't know about that. I've obviously heard the milk thing like a lot of people, but I don't know why it works. And I'd love to know about all of that and the tolerance thing, building up tolerance. And I think perhaps most importantly for me is I love spicy things very, very much so, please.
That's kind of good to know because I assume that everyone already knew the front part of this. So I focus more on the back part, but that's okay.
I mean, I guess unless you say it and then I'm like, oh, I did know that, but I don't think I do. I don't, it's not coming to mind.
Does the word capsaicin mean anything to you?
Oh, okay. Only sort of, because in my other podcast for your life, we did a spicy for your life a couple of years ago.
How exciting.
Where we just supposed about the spiciness of things. And we didn't know any of that stuff. And so we were like, what could it be that makes things spicy? And talked about it. And then one of our listeners did like message us or something and said capsaicin. Now I could not have said it back to you. I didn't remember what that word was. I think we just said like, maybe there's some acid in spicy food. We're totally guessing, but that's all.
Well, I'm taking out the guesswork. There's a molecule named capsaicin. It's an organic molecule, so it's mostly made up of carbons and hydrogens, and then there's some oxygen, nitrogen mixed in there.
Oh, man.
The basics of what it's made up of is carbon and hydrogen.
Okay.
That's why it's known as an organic molecule.
Okay.
But it has a base unit that is actually recognized all over our bodies. So do you remember when we talked about functional groups?
Yes, I do remember that word, that phrase.
So functional groups is just a special arrangement of atoms in a specific way.
Okay.
And those functional groups have similar properties no matter what molecule they're on. So one functional group that a lot of people have heard of is an alcohol group.
Mm.
That's an oxygen and a hydrogen.
Okay.
And it's an alcohol group, and it has a similar functionality no matter where it is.
Okay. That's where the function part comes from. Is that like they're arranged in a specific way that is recognizable in different things or whatever, and it ends up having a similar function in all those settings?
Yeah.
Something like that?
That's a great way to put it. Yeah. Has a similar function in a lot of different settings.
Okay. Sweet.
So, like if you're an organic chemistry student, you're going to learn how different functional groups react or how to make them.
Mm.
Okay. That's a functional group. So you have that information.
Yeah.
Now, a capsaicin molecule has this base unit that is recognized all over our bodies. And it's a 6-membered ring, so 6 carbons in a ring. So it's basically just a hexagon shape, if that's easy for you to imagine.
Okay.
And on that hexagon, there's 3 functional groups attached. 3 functional groups bonded on.
Okay.
2 of them, they're next door to each other. They're there all the time, no matter what. You have an alcohol group, an OH, and then next to it you have an ether group. And that ether group, if you're an organic chemistry student, hopefully you remember. For the rest of you guys, it's just a carbon bonded to an oxygen, bonded to another carbon.
Okay.
So I don't know if it really matters, but so those 2 functional groups are always there.
Okay.
And then across from the alcohol, there's a different functional group. And depending on the function of the molecule, that functional group changes out. So it's not always the same. It can be any group of carbons, hydrogens, oxygens, nitrogens. It'll be an organic functional group or an organic chain of some kind.
Okay.
So that base unit with the interchangeable other group, that class of compounds is known as vanilloids.
Vanilloids?
Yes.
Like vanilla, but not?
Yes.
Okay.
And the reason it's known as vanilloids is because vanilla is in that group.
Ah.
So vanilla is in that group.
Okay.
Vanilla has a very basic functional group attached to it. And that smell that we recognize as vanilla is, the chemical name is vanillin with an N at the end instead of an A. I worked with that in the lab where I did organic research, and it smelled so good.
Yeah.
So vanilla is in that group. But if you change out the simple carbon oxygen functional group on vanilla for a very long chain with some double bonds, a nitrogen, and oxygen mixed in there, you get capsaicin.
Mm.
Also in this group of vanilloids is gingerol, which is in ginger, and there's a close but not exactly the same structure that's in pepper, like black pepper. It's all over everything. And just changing that one group out for different things can make it interact with their receptors differently.
Got it. Okay. Okay, can I ask a question real quick?
Yes.
Could I kind of make sure I understand what shapes are what and which groups are where, so I don't get lost later?
Yeah, I think that's a great idea because this is the big organic chemistry idea.
Okay, so the first thing we have is a hexagon of 6 carbons.
Yes.
And then on one end of it, we have the alcohol group, which is a carbon and an oxygen and a hydrogen.
Yep.
Right? Okay.
Mm-hmm.
An oxygen and a hydrogen. And then next to it is an ether group, which is a carbon, an oxygen, and another carbon.
Right. So the first carbon in that chain is the carbon on the ring, bonded to an oxygen, bonded to a carbon.
Got it. Okay, got it.
And I can post a picture of this up on the internet.
That'd be awesome. And so on the opposite side from those two things, those two buddies, is another group that can change out as long as it's an organic functional group.
Right.
It can change out and be different things, but the whole thing is called a vanilloid.
Yes.
Okay.
That's right. The vanilloid is the type of, they just sort of characterize, okay, all these have this base unit of the 6-membered ring with an oxygen and an alcohol on one side and the ether on the other side. And then there can be anything over here opposite from the alcohol, anything at all. And that's a vanilloid.
Got it. Okay, sweet.
Okay, so, but I do want to clarify, it's not as if scientists go in and change those out for one to another. They could, but a lot of these just occur in nature with that base vanilla unit.
Mm-hmm.
And then they have these other things on them that make them interact with the receptors differently.
So it's more like they recognize this pattern over time of like, hey, this thing, they've all got like a good amount of these things that are similar. And then this part over here is different. But it's kind of like, well,
right.
Let's put those into a category so we know what we're talking about.
Right.
Okay.
So, and I posted recently a picture of the molecules in the thermochromic mug episode, and people loved it.
Mm-hmm.
They were very excited.
Yeah.
And I thought maybe molecules would be boring to look at. But now that I know that people like having that visual aid, I'll go ahead and put some of these structures online so you can see the similarities and also the differences between the different molecules.
Yeah.
I did not know that capsaicin and vanilla had the same base unit.
Mm-hmm.
I didn't know that. But you see this theme a lot in organic chemistry where you change out one group or you take the mirror image or something small, you go from a cis to a trans bond, like we talked about in the margarine episode, can change a lot about how something functions.
Mm-hmm.
You know, we talked about the limonene, which can be either orange smelling or lemon smelling.
Right.
And then there's this vanilla, capsaicin. Those interact with our bodies very differently. But they have the same base receptor unit.
Yeah, that's crazy.
It is crazy. So that's kind of something I wanted to bring home is changing out a functional group, changing out a chain of atoms or the way they're arranged can really make a difference.
Yeah. And it's nuts too because I think to us regular folk, I think thinking that like one part of it's different would mean I just wouldn't assume there'd be such a huge difference in terms of like taste or whatever other, relationship we have with it that we've experienced in our lives. Difference from like vanilla to like something spicy or whatever.
Right.
It just seems like in my mind, if someone just pulled me, I would think, oh, the spicy molecule is probably like crazy different looking than like vanilla, like nice and, aromatic kind of sweetness to it or whatever that we associate with it anyway.
Yeah, I know. I think that's really one of the beautiful parts of chemistry is just a little change can make a big difference. And that means we have the power to make really beautiful and unique things from similar groups of molecules. Kind of what I talked about when the person asked me what my favorite element was.
Mm-hmm.
Okay, so that's the basics of what capsaicin is.
Okay.
It's an organic molecule. It has the base unit of the vanilloid. It's in that group. And it has a different side chain. It has a long chain of carbons with a double bond, nitrogen, oxygen, splits off at the end kind of into a Y. That's capsaicin.
Okay.
And capsaicin interacts with and triggers the pain and heat receptors on our tongue and in our mouths and even on our skin. So even though the molecule is not warm temperature-wise,
mm-hmm.
the receptor that it triggers as a pain receptor from heat. So it sends a signal to our brain that the thing is hot, that is spicy.
Huh.
And our brain takes that as bad, pain. This is not good. And that's why our nose and eyes water and we sometimes cough or really, really want something to cool it down, is because we're trying to flush the bad thing out of our body.
Interesting.
Isn't that crazy?
So you said it's like the same as a receptor that would cause that?
It's the same as a receptor that would be able to tell that you drink too hot tea, or that your pizza's too hot, or other kinds of pain.
Uh-huh.
So that's why it triggers as heat.
Got
heat
it.
and pain receptor.
Got it. Wow.
I know. Isn't that amazing?
So weird. It's also so funny to like, this is maybe the second or third time this has happened where a topic that Jason and I have just spitballed about on Podcast for Your Life with no even chance of getting anywhere close to the answer. It's funny then for it to come back around, because I obviously did not know you were going to pick this and that we'd talk about it. It made sense eventually because it's a great question. But it's just so funny to like come back around and be like, man, I have so wondered this and have had such stupid ideas of what was causing it.
It really is crazy. And I love learning about these things that people wonder about. It's perfect that you and Jason talked about it, because that means that other people think and wonder about it too.
Totally.
So that's exciting. Okay, so those are the big chemistry takeaways that I want you to have for today.
Okay.
So you've kind of already explained the first part, but do you want to kind of give a review on the receptor situation?
Yeah, that'd be perfect. I'll just add on to my like double check explanation thing earlier. So we have the vanilloid group, right? Which is that like recognizable kind of pattern category of types of molecules or whatever.
Right.
And capsaicin is the spicy one. And it has
one of the spicy ones.
One of the spicy ones. Okay. Is it like the most common?
There are other spicy ones. Oh, yes. I think capsaicin is definitely the most common.
Okay.
But there's another compound that looks just like capsaicin, except it's missing one carbon. At the end where capsaicin splits into a Y, it doesn't.
Uh-huh. Okay.
Missing one carbon, and it's half as spicy as capsaicin.
Oh, interesting. That's weird.
Isn't that weird? It's so close. Chop off one carbon, and you cut the spice in half.
Weird. So I remember the shape, and I think partly it's just remembering a lot of the like letters and shapes this time in my head. But the little chain that splits into a Y off of the vanilloid, you said it's nitrogen and...
It's a chain of carbon, and at one point there's a nitrogen and there's an oxygen, but it's mostly carbon and hydrogen.
Okay.
That's an organic molecule. It's usually mostly carbon and hydrogen. So it's just an organic carbon chain.
And then it has a split off, which is important, especially for determining it compared to like other molecules that are similar, like the other one that's spicy, you said.
Right.
Okay.
Mm-hmm.
But most importantly, that shape, that little chain coming off in our mouths and our bodies and receptors interpret when they interact with this molecule, capsaicin, they interpret it as the same thing as when we eat or drink something very hot that isn't just hot, but is a level of hot that we experience pain from.
Right.
So obviously we love to eat hot food, but like hot, where we start to do the like, or the, all those things like burn the roof of your mouth with pizza, that kind of stuff. And so.
And I don't,
I was going
to say, I don't know for sure if it's only a hot pain receptor, but it is a heat and pain receptor. So I think it's when those two sensations come together, but I don't know a lot about biological functions, so I'm a little fuzzy on that, but it signals the same thing as heat and pain.
Got it. And it makes sense that we have some level of both those things in our mouths, because separate from the existence of spicy foods, it might be good for us to know as humans that are trying to keep ourselves alive for generations and generations that, hey, this thing's super hot and it's causing pain. And that's bad because you might be damaging your body. So it's like,
Right. Exactly.
it makes sense that we have those. But what's so weird then is that this little molecule triggers that, even though it's not actually hot. I mean, it could be, but you could also just have a cold, spicy thing.
Right.
And it's not actually painful in the real way. It's not like it's actually burning you and,
Right.
Melting your inside your mouth or something like that.
But it just triggers that.
It just triggers that. So it's a false alarm kind of deal.
Right.
Weird, dude. That's so weird.
So weird. I know. It's amazing.
Our bodies, our mouths are getting a false alarm.
Are you ready for it to get crazier?
Yes, I'm ready.
Okay. So, because capsaicin triggers our pain receptors, you can use it as a pain reliever. You can spread it on your skin or wherever, and it will trigger your pain receptors, keeping them from triggering further and just be interpreted as heat. And you will not feel the same kind of pain. It's a pain reliever.
Weird. So you're kind of telling your body, like, hey, feel heat instead of whatever it is you're feeling. So, like, like, what kind of pain could I use that with? Like, if I scraped my arm or something, or I don't know.
I don't know. Let me look it up. I just looked up what is capsaicin cream good for. So, full disclosure, this is from Google. And it says that it is a topical cream used for temporary relief of muscle or joint pain caused by strains, sprains, arthritis, bruising, or backaches.
Huh.
It also can be used to treat nerve pain in people who have shingles.
Dang.
But that is from Google. I did not check those sources.
So allegedly, that's what it could be used for.
There's another vanilloid that's found in cacti that actually has the same base unit, but a much more complicated group where the capsaicin chain normally is, where that switch out chain is. And it is some crazy number, like 100 or 1,000 times more powerful as a pain relieving cream than capsaicin is. But can you imagine what that would taste like in your mouth? I feel like it would be torture.
What the heck? Yeah, seriously.
But I don't know for sure. I don't know if people taste it or what, but they referenced it in a textbook that I was reading that said it's significantly stronger and has been used as a pain reliever for a really long time.
Dude, interesting.
Okay, well, it gets even crazier.
Oh, wow.
When I was looking some of this up, I found a list of papers about capsaicin and vanilloids, using them in medical research to treat headaches and bladder disorders. So not only is capsaicin useful for pain cream, but they're using it in research to treat other kind of medical conditions.
Whoa.
So peppers are kind of magical.
Yeah, that's crazy. And we just love the flavor. And like, or some of us do, I guess. But like, it's crazy that they have so much more potential than just like tasting good.
I know. It'd be like if you found out ketchup could save your life. Kind of.
Yeah.
That was how it feels when I was reading it. I couldn't find any in-depth articles about how effective that had been or anything, but just that it was even being considered was really amazing to me.
Yeah, seriously. Man, interesting.
Super interesting, but there's more.
Whoa.
So these pain receptors in your mouth that detect hot food and capsaicin, the more often you activate them, you can actually do damage to them. So you can build up a tolerance to heat by just activating those more and more because you're kind of destroying them.
That is crazy.
I know.
That's so nuts. Whoa. That makes sense because I have definitely always liked spicy food, but over time have definitely been able to increase how much I can handle, so to speak.
Right.
I'm not trying to hurt myself at all. It's not a contest, but it's just like, I like spicy food. And so then it means that over time I've had to like slightly increase, what level of spicy I get at the Thai restaurant or whatever.
Mm-hmm.
And that's crazy. So I've just been damaging my receptors over time.
Right.
Probably.
So you just need more to get the same experience.
Interesting.
Mm-hmm.
Dang.
Okay. And are you ready for the last fun fact?
I'm ready.
That chain that comes off of the vanilloid base area is long, carbons, hydrogens, not superpolar. Is non-polar chain.
Okay.
You want to know what else is not superpolar?
Milk.
Milk is not superpolar. So the long chain on capsaicin and the long fatty groups in milk are going to surround, I guess I should say, the long fatty chains in milk are going to be able to bond with, interact with, have intermolecular forces with the long chain in capsaicin, whereas water just basically moves it around but doesn't really dissolve it at all. So water spreads the heat in your mouth and milk cools it.
Gotcha. Because water is polar. And so it might move some things around, but it's not probably going to be able to interact nearly as well.
Right.
Man, that makes sense.
It won't surround the molecule or anything. The molecule just kind of hangs out, almost like if you're swishing around oil in your mouth with water, is not really going to get it out.
Right. They're just going to kind of stay separate in their own ways. Yeah. Weird.
So theoretically, you could just drink oil and it would have a better effect, although it'd be less pleasant than drinking water to get the capsaicin out of your mouth.
Right.
Milk also has a protein called casein, which binds with capsaicin.
Mm-hmm.
That makes it even more effective at getting that capsaicin out of your mouth and cooling it down.
So it's got the non-polar fatty stuff, fattiness, which can surround and interact with the non-polar chain of capsaicin.
Right.
And then it's got casein in the milk. So which that helps a lot in casein the capsaicin. That was rough. Gosh.
That was actually very clever. Didn't even think about that coming at all. So
I was looking for one. I was just trying to find some anywhere.
So, and if you want to learn more about polar and non-polar things and why they don't interact, you can learn about that in our very first episode, How Does Soap Work? Because we talk about that.
It's a good one.
So that's it. Now there's no more. That's all of the information on capsaicin I have for you this week.
Nice. That was awesome. Dude, I loved that one.
I'm so glad. I really like this. I don't like jalapenos themselves.
Mm-hmm.
Just eating them, I don't, but I like them as spices.
Yeah.
In my guacamole, on my jalapeno chips.
Yeah. I've gotten into a stretch of my life now where if I can't have every meal be spicy, then I want it to be. I think it's also a combination of that and the fact that somehow it doesn't really affect my stomach in a negative way.
Oh, yeah.
And so I'm I enjoy the spiciness. I love that experience. It tastes great. So curries and salsas. Jambalaya. All the things that can be spicy that different food ethnic genres that are known for kind of their different spices and stuff like that. I just love it. And it's kind of become the types of foods that I look forward to eating the most or whatever. But now it's even cooler to know the chemistry behind it.
Mm-hmm.
Because I eat them so frequently, I'll probably be thinking about it all the time.
That's so exciting. I'm so glad. And it makes me wonder if that's why kids don't like spicy foods usually, is it's just too much for their undamaged receptors.
Mm-hmm.
Just a thought.
Yeah.
So now that we've reached the end of our fun facts list, I'm going to share a fun fact with you from my week. I'm mixing it up. I'm going to go first.
Sweet. I love it.
My fun fact for this week is I started playing a video game.
Whoa.
I'm not really a video game person.
Totally. Yeah, you're really not. I think Pokemon's the only one I've really known of that you really love to play, classic, old school
Well,
Pokemon.
this kind of reminds me of classic old school Pokemon.
Oh, nice.
So I've been playing Stardew Valley, and it just feels kind of like that. The aesthetic, the noises that your little feet make in the grass. And so basically I'm just building a farm. Me and my significant other started whenever we couldn't see each other. That was how we would have dates,
Oh, nice.
We would meet up on the farm. And now I'm playing my own farm also by myself, and it's just so peaceful. I don't know what it is, but it's so calming and peaceful and satisfying. You feel like you've accomplished something with your day, even though it's the middle of summer break and I haven't.
It's like a little like digital Zen garden.
It kind of is.
That's what it sounds like. I've got one that's not intentionally opposite. Just to give the caveat at the beginning. But
so you're trying to show me up, or
not at all. In fact, people will probably be like, I'd rather do Melissa's thing. So for a couple weeks now, my wife and I have been doing a weekly digital detox day.
Oh yeah,
which Melissa knows about because we told some people that, hey, we're doing this, so that way if you trying to get a hold of us, that's why you can't get a hold of us, but call us twice in a row if it's an emergency. But
I was about to say, I know the secret trick for how to get a hold of you that no one else knows, but then you just told everyone. So
yeah, because we don't want anybody to not tell. I mean, like, hopefully they wouldn't do that if it's not an emergency, because that'd be like crying wolf. So just don't do that. But we've been doing a digital detox kind of thing once a week, and we've only done 2. So long-term enjoyment of it is TBD. But I would say for the first 2 times of doing it, I've found it super, super enjoyable. And we do ours on Saturdays, which for our schedule now works great and wouldn't maybe work for everybody. But it's been so nice. We also just kind of use that time to hang out together, do analog things together, go on walks, that kind of thing, read. And it's super nice. I think there's something really great about just taking a break from all things digital. And it can be really hard to do that during the work week. I mean, many of us, especially now.
Right, especially now.
Way more dependent on our machines and stuff than usual. But there also is tons of our machine and phone usage that's not work-related, that's not super necessary. And I've noticed it really bogs me down. And M feels the same way. So it's been really great. It's maybe not for everybody, but if you have ever felt that kind of bogged downness, I would definitely recommend trying some sort of digital detox, a full day of it, maybe every week or every other week or something like that you can do. At least in my limited experience so far, it's been really cool. So, yeah.
Well, thanks for coming to this digital meeting in this digital age that we're going to post on a digital media, since you hate digital things. Just kidding. I know you don't. But really, thanks so much for being so excited about our topic. This was a really fun one for me to do, and I'm glad you enjoyed learning about it so much and that you had already wondered about it.
Yeah.
That made it even better.
Yeah, it made it fun for me too. I mean, all our topics are fun, but it made it more fun too to be one I've really wondered about. So thanks for
it really was.
Thanks for teaching me.
Oh my gosh, you're so welcome. And thanks to all of you listeners for coming and learning about what makes jalapenos hot and also magical. Oh yeah, and let us know any of your other ideas, because this was a really fun one, and it came from the wondering of my brother's brain, and he just sent it my way, and now here it is. So let us know.
So Melissa and I have a lot of ideas for topics of chemistry in everyday life, but want to hear from you. Just like Melissa's brother, if you have questions or ideas, you can reach out to us on Gmail, Twitter, Instagram, Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share your thoughts and ideas. If you enjoy this podcast, you can subscribe on your favorite podcast app. And if you really like it, you can write a review on Apple Podcasts. That helps us to be able to share chemistry with even more people. If you'd like to help us keep our show going and contribute to cover the costs of making it, go to ko-fi.com/chemforyourlife and donate the cost of a cup of coffee.
This episode of Chemistry for Your Life was created by Melissa Collini and J.M. Robinson. References for this episode can be found in our show notes or on our website. J.M. Robinson is our producer, and we'd like to give a special thanks to V. Garza and S. Flint, who reviewed this episode.